This is a lesson on the Doppler effect with sound waves in the simple harmonic motion and waves unit. In prior lessons, I had talked about sound waves and their properties, and they have a velocity, a wavelength, and a frequency. And the frequency is what we're going to be interested in with the Doppler effect. The Doppler effect is an alteration in observed frequency due to a motion of either the source or the observer. And you may see this as different versions in different books. This is the version I've chosen, and it correlates with the OpenStax University physics situation. What you see is that there is an observed frequency. And I put a picture up here where the red dot up here is the source. There's some sort of source being, so you may imagine the typical example brought up for this is like a police siren or an ambulance or a fire truck, that sort of situation, where we have a source and it's moving at a speed where you can recognize that the sound is different before and after, before it passes you and after it passes you. So there's a source and there's an observer. There may be an observer ahead of the source or an observer behind the source. And that observer may or may not be moving themselves, okay? So there's an emitted frequency, some frequency of the source, frequency source, and there's some sort of observed frequency, either in front or behind. And again, the source may be sitting still and the observer moving. That may be a situation that happens. There's an observer speed and a source speed, and the speed of sound is in here. This V is the speed of sound. VO is the observer, and VS is the source. This is the source, this is the observer. And you can see that there's pluses and minuses in here. There's a plus-minus situation and minus-plus situation. I provided this chart from OpenStax because it kind of overviews all of the situations when they're both stationary. Well, when they're both stationary, there should be no shift. But you can see that if like the observer is stationary, we'll say V observer equals 0. If it's stationary and just the source is moving towards them, like a police siren, the frequency of that source will be perceived as increased because of that relative speed between the source and the observer. And that's because the peaks of the sound ahead of the source are being pushed together, and so that frequency will increase. We see an increased frequency. And if the observer is behind and the source is moving away, then the peaks are pulled apart. There's more distance between them, and you will see a lower frequency. And that's how I think about this equation. I don't think necessarily of this situation. There's a lot of things to remember, and it's just a big hassle. What I remember in this situation is imagining the situation. Do I expect the frequency to increase based on the relative velocities, or do I expect them to decrease based on their relative velocities? You will see this topic again with light, and there is redshift and blue shift, like out in the cosmos. That's how we measure whether things are moving towards us or away from us, is we measure the frequency, and we know what the frequency should be, and so we can measure the difference of speeds between those two objects. There's no relative speed here. You will see V relative used in that situation, but there's no relative speed here. We really have to think about, do I expect the observer's motion to increase or decrease the frequency? And do I expect the source's motion to increase or decrease the frequency? And why it's a plus minus on top, that should make sense. On the bottom, it's a minus plus because, for instance, let's say that the observer is at rest and the source is moving. So if I have V observer equals 0 and V of the source not equal to 0, let me plug in these things into the equation. I'll still have the frequency of the source. The frequency of the observer is 0, so I'll go plus or minus 0 on top. And then I'm going to have V and the V source. And if the source is moving towards the observer, then I expect the observed frequency to be larger than the original frequency. And in order to get a larger number, I need a smaller number overall in the denominator, and that corresponds to the minus sign. If I wanted a shift upward, I would add a plus in the numerator, but it corresponds to a minus in the denominator. And again, you can see all the different situations down here. I go back to, do I expect the motion of the observer to shift the frequency, and in what direction? And do I expect the motion of the source to affect the frequency, and is that an increase or decrease? And pick your plus and minus signs accordingly. To imagine these things, I picked a couple of pictures from some sources that I actually lost. I don't know where these are from. But here's a stationary source. You can see that the sound on both sides are equal to one another. All right, that's the same frequency. When the source is moving towards the left, we can see that here. When the frequency becomes larger, we call that a blue shift, and when the frequency becomes smaller, we call that a red shift. And what I'm going to note as well is because the speed of the sound is the same, the sound is the same, then the wavelength also changes, and you can see that between these two there's a different wavelength for them as well. And that's why we call this a blue shift and a red shift, because if the frequency changes, the wavelength of the light changes, and wavelength corresponds to colors for us. Again, here's the ambulance. We can see if the ambulance is moving towards the observer, we get a high frequency. If they're moving away from the observer, we get a low frequency. And that's sort of the opposite situation below, where we have the observer in the middle and the source on one side and the source on the other. If the source is moving away from the observer, we get this ooh effect. It goes down, the low frequency. That's what we call sort of a red shift. If it's heading towards, we get this wee, it gets higher, and that's what we call a red shift or a blue shift, or a higher frequency. And so imagine in that situation, you can do in your head, but I think more in terms of these wavelengths. Do I expect the wavelengths to be closer together, or do I expect them to be farther apart? And that tells me if I expect the frequency to increase or decrease. The problem I picked is fairly simple. I may do a more complicated example in another video. It's called watching a bird. A bird is flying directly toward a stationary bird watcher. Okay, so I'm already seeing that there's a source and an observer, and one is stationary and one isn't. The bird emits a frequency of 512 hertz. The bird watcher, however, hears a frequency of 290 hertz, 1290 hertz. What is the speed of the bird? Okay, so let's draw a bird watcher here. There's the bird watcher, and the observer is stationary. The velocity of the observer is 0. And they hear some frequency, 1290 hertz. But that wasn't what the bird emitted. Let me put the bird in the air over here. There's a bird. The bird is flying towards the velocity of the source. This is the source. This is the observer, and this is the source. The bird is flying towards the observer, and the frequency of the source was 1250 hertz. So there was definitely a shift in here. We see that there is a shift upwards. So when I look at this equation, I want to solve for, actually it says what's the speed of the bird. So I'm going to be solving for V source. But I'm going to set the equation up first before I do any algebra, because I have to figure out if this is a plus or a minus, and I can simplify the top as well. So the frequency of the observer equals the frequency of the source. V plus or minus the velocity of the observer, which is 0. So I'm going to leave nothing there. And we're going to divide by the velocity of the sound plus or minus the velocity of the source. Which do I want? Well, what I notice is that I have a higher frequency. I'm perceiving a higher frequency than the original one. And in order to get a higher frequency up on this side, I need to make the denominator lower in value. The way I can make the denominator lower in value is to subtract the speed of the bird from the speed of sound. If I make this smaller, that will make that larger. So Now I have my equation set up. I'm going to end up solving for velocity of the sound. The first step I'll do is divide by the frequency of the source on both sides, and you'll see how that will help me in a second. V minus V source. And I'm going to invert this equation. I'm just going to take both sides and flip them over. So I get frequency of the source over frequency of the observer, right? I just flipped that. And then I'll flip this side as well. V minus Vs over V. And you may notice here that the V can cancel on both. If I distribute the V in the denominator to both terms, frequency of the source over frequency of the observer equals 1 minus velocity of the source over the velocity of sound. And you could put bird here, but we're solving for that variable. We're still solving for that variable. Let's do one more step. The velocity of the source, I'm going to subtract it to this side and Fs over F over on the other side, and then multiply by V on both sides. So you can check my algebra that I did this correctly, but I am pretty confident that that is the next step of algebra. And when I plug the numbers in, I take 343, right? It's the velocity of sound, and we're just going to assume it's on a regular day. So we're going to say 20 degrees Celsius. 1 minus the 1250, right? The frequency of the source is 1250. The frequency of the observer is 1290. So I get 1 minus that times 343. And the velocity of the bird, the source, I found to be 10.636 meters per second. You may find, which seems like a good velocity for a bird. That's a fine velocity. If it was too much, I would be concerned. And if it was negative, I would also be concerned. But this seems like a fine velocity for a bird. You may find other problems where you need to do more complex thinking about this. And again, go back to what effect do you expect to have the motion of that object to have on the frequency. If it's toward, it will increase. If it's away, it will decrease, and you need to pick your signs accordingly. Whatever it does in the numerator, it will do the opposite in the denominator.